Everybody, I'm Mitchell Klusty. I'm filling in for Dr. Baumgartner today because he had another presentation he had to give at this time. So I'm going to be talking about large language models and how they apply. I work with the Center for Applied Artificial Intelligence under Dr. Baumgartner with my colleagues here. So yeah, let's get into it. So in this presentation, we're going to go over some of the basics of LLMs, how you can customize LLMs, what multi-modal LLMs look like, and how you can connect LLMs in with larger systems and agent-based systems. So right off the bat, what are LLMs? I'm sure everyone in here has worked with ChatGPT or maybe Copilot. Everyone's worked with an LLM, I assume. But that's basically the intention is you give it text and it can respond with text. Yep. So you give it an input text and then it responds with an output text based on your query, and you can prompt it in specific ways so it can give you the response to whatever input you give it. So there are a lot of models out there. What are some of the key differences between them? Each base model, so like ChatGPT, GPT 3.5 versus Llama, which is made by Meta, each one of those has their own custom architecture. And those are very hard to train, so they're only really made by large organizations that have a ton of money and a ton of resources to train models like that. But in between each models, there's differences in the number of parameters that they have in there. So that's the size of the model and the context length that you can provide the model. So that's how much information you can give it at one time before it starts not being able to process that information anymore. So how do those factors affect the models? If you have a larger model, which has more parameters, the cost of using and training that model is going to be higher. The quality is going to be higher, but the speed is also going to be lower. And then with the increased context, you can put more information into the model, so that obviously means that you're going to have higher quality because you get more information in there, but also because you have more tokens going in, that's going to increase the cost, and the speed is going to go down because there's more processing involved with using that input. So just as an example of a progression of a model over time, Llama 2, which was released last year, it started off with models that were 7 billion parameters, 13 billion parameters, 33 billion parameters, and 70 billion parameters. And then Llama 3.0 had significant performance improvements, and that was released earlier this year. And its model sizes were 8 billion and 70 billion. And then Llama 3.1, which was released in July, is a slight upgrade to that has a lot of better features in there. And its sizes were 8 and 70 billion, just like Llama 3. But then they also introduced a 405 billion parameter model, which is obviously a significant increase in the size of the base model. And then Llama 3.2, which was released earlier last month, that has smaller models that are sized 1 and 3 billion parameters. So those two models of that specific size can be used on computers that have less resources, not as strong GPUs, and they can be used in more distributed applications. And then they also released an 11 billion parameter model and 90 billion. So those are improvements over the smaller and medium-sized models of the last versions. And then the context length, how that has grown over time. Llama 2 had a context length of about 4,000 tokens, and Llama 3 had a context length of about 8,000 tokens. But then with Llama 3.1, they increased the size of that from 8,000 to 128,000, which is a significant increase. And then the release from 3.1 to 3.2 is the same context length, so there's no improvement there, but that was only a month apart, so kind of makes sense. So some limitations of LLMs in the way that you interact with them. So generally, if you want to have your text in, text out, an LLM won't really be able to tell you information that is new or information that it wasn't trained on. So like if I were to ask it, what is the weather like in Lexington today? Then it would give me a weather report, but this weather report is not accurate because it doesn't have access to what the weather is in Lexington today. So it gives me information, and it thinks that this information is right, so it presents it to me as if it's right, but it doesn't actually know what the information of that model is, or the weather is, sorry. It just knows what a weather report looks like. So it gives me a weather report in the format of a weather report, but none of the information in there is correct. So how do we give the model the information that it needs to kind of combat that limitation of it not knowing something, and we want it to know that? So some methods that we're going to talk about for that are adapters, RAG, and tool calling. And We'll get into the specifics on what each one of these are in a second. So adapters. Adapters are in addition to the base weights of the model. So like you are making changes to specific areas within the model and adjusting how those weights are and merging the new weights of the adapter together with the base model. So this doesn't create a new model per se, but it creates a standalone piece of a model that you can then merge into the base model and create a change model with information that it kind of makes the model a specialist on the area that you want to talk about. So you add this new knowledge in there, you train it the same way that the model was trained, and then as you deploy it, you're able to then add or merge the weights together with the base model, and then the output is going to be affected by those weights. And you can actually, you can add multiple adapters at the same time and weight the specific values of how strong you want each adapter to be. So if I was to train an adapter on one specific area and then also train it on another specific area, so like take networking and machine learning. If I wanted the model to be smarter in machine learning, then I could turn on the machine learning adapter. If I wanted to be stronger in networking, I could turn on the networking adapter. And if I wanted to be smart in both, I could turn both of them on and merge them all with the machine or with the model, and then it could be as good in machine learning and networking. But this trade-off there is that you're making the model bigger as you add more adapters, so then it costs more, and you'd want to really use the things that are more specific to the query that you're asking. So as an example of one that we've used in our projects, we have a project that we're working on right now with the Department of Social Work, and they're trying to set up a system where they can use an LLM as posing as a teenager that is going through some suicidal thoughts or some sensitive topics that the model generally has guardrails to not talk about. So the model, if you talk to just the base model and ask it to if you instruct it to pretend like it's a teenager and say that it is having suicidal thoughts and it's talking to a social worker, then the model is going to say something like, I can't discuss sensitive topics like this, let's talk about something else. But those guardrails are in there for a reason, but we can't really do that if we want this project to work with an LLM. We can't really just accept that the model doesn't work. So we can make an adapter that's called an obliterated adapter. So it adjusts the weights of the model and removes those guardrails. So then when we ask it the same question, it will actually talk as if it is a teenager that is struggling with that type of situation. The next technique that we're going to talk about is called RAG. So what this is it allows you to introduce new information to the model in what's called a vector database. So you store information outside of the model, and then you're able to find that information through a process that we're going to go into, and then use that as context to provide the model information. So whereas with the adapter, you wouldn't really be able to train that with for the weather issue, because if you train an adapter with information on the weather in Lexington, then it might know about the weather in Lexington of today, but then that's going to change tomorrow, so you need to train the adapter again. But that's not really a sustainable solution. That's where something like RAG would come in, where we'd be able to, as we go, add new information into that vector database and be able to pull it out as we need. So for normal search, if we want to look for the circulatory system in the set of unstructured data, we have just a list of body parts and organs and stuff, and circulatory system is not in there, but obviously there's stuff like heart and capillaries and veins that we would want to be able to find from the circulatory system if we were to search for circulatory system. So when we look for it, it's not in there. That sucks. That's how normal search works. But then with RAG, we can take this unstructured data and vectorize it down into a very large set of floating point numbers that represent the semantic qualities of the data. So we encode it into what you can think of as a coordinate plane, basically, except that instead of 2 dimensions, it would be something like 760 dimensions. And it might look something like this, where it groups all of those points into a vector database on the right. So now, if we want to search for that, we do the same process, and we vectorize the circulatory system in the same way that we vectorized all of the data that we put into the vector database. And then we get coordinates in vector space of circulatory system in the same vector space as all the data that we encoded. and then we find that it's there, for instance. So then we're able to do a RAG similarity search. So we take the data that we've encoded and the data that we just encoded, or the query that we encoded, and find a range of data that is most similar to that encoded query. So in this example, it found arteries, blood, heart, capillaries, and veins, which are all related to the circulatory system and are the most related documents in this database. And if we want to do that for a respiratory system, it might be up there, and it might grab oxygen, larynx, lungs, and nose. So then in a real situation, you wouldn't do this on something as small as capillaries, heart, blood. You would actually have documents that have information that are like longer sections of information that you would want to query and be able to identify. So you might ask it, like, tell me about this specific heart disease, and then you would have information about heart diseases encoded in these different points on the vector space. So if I were to ask it, tell me about the circulatory system, it grabs all this data, pulls it down, and then gives me information based on those documents that it pulls down. So in application, one project that we're working on is a collaboration with the College of Agriculture. So they have a lot of information that they want to make accessible to farmers around the state and to the extension agents in different communities so that they can have a tool where they have easy lookup of information so they're able to help the farmers out and answer questions pretty easily for them. So what we did is we took College of Agriculture data, and this is in the form of websites and PDFs, and we can encode that into a vector database. And then we're able to ask it specific questions about their data and then find the semantically similar entries into the database and extract those out and pull out the relevant information to the question that they ask and then feed that into an LLM, and then the LLM can respond based on the information that we gave it. So our next method is called tool calling. And what this allows you to do is it allows you to connect an LLM into code. So you can define your own tool, which is just a set of Python code, any type of script, and you can then use the LLM to extract specific fields that will be input into that code and run the code on that input. So going back to the weather question, if I ask it what the weather is like today, I might have a set of tools that I've defined where one of them is the weather lookup tool. And I can give that tool a description that is looking up the weather. So I want to tell it that it can look up the information about the weather for a location and a date. So it's able to take the description that I give of that tool and identify based on the query which of the tools it should use to answer the question. And it looks through those, finds that the most relevant answer or tool to the question is the weather lookup tool, and then it looks at what is the structure of the weather lookup tool. And the weather lookup tool requires a location and a date to give a response. So then it looks back at the query and it says, what is the location? What is the date? It's Lexington today. So this is an older presentation. I didn't update the date, but it would extract what today is from like just a Python code, and then it would get, I think it's October 2nd today, so it would pull down October 2nd and then request the weather in Lexington on October 2nd. So then that would go out to an API call, and it would be able to pull the information down and give a response to what the weather is in, like today, October 2nd in Lexington, Kentucky. So combining tooling with RAG, what we can do is we can set up multiple vector databases side by side and then describe each of the databases and what the data looks like, what the general information in the table is. So if I have these different databases set up, which are different organizations that we've worked with and set up databases for, then I can ask a agriculture question, and it will know to go to the agriculture data. And that's done by just the description of the tool. So the LLM looks at the description and can identify which one of them is most closely related to the query. And then if I have a question about SELT, for instance, then it would go to, based on the description, it would find that SELT information is most related, and it would pull out data from that, feed it to the LLM, and then that would give me the output based on the response. So when do you use each one of these techniques in practice? When do you use adapters versus RAG versus tool calling? Adapters are really good at changing the way that the model speaks. So if you want to have the model talk in a certain way that it doesn't really talk now, if you want to add specific knowledge and make it an expert in a certain field, and it's information that is not going to change and you won't have to retrain the adapter, then that would be a good way to go about doing it. If you want to add information that is changing, add information that doesn't have to exist in the model, you don't have to you don't have to change the model in any way. You can just add a standing set of information for the model to be able to look at. That's when you need to use RAG. And then tool calling is when you want to connect an LLM to code. So all of these can be used in conjunction. It's not one or the other, but each of them, especially adapters and RAG, can be used in specific ways that you should focus on what is the best way for my problem to use this. But then RAG and tool calling and adapters and tool calling can often work together in tandem to give you the best result for your project. So another way that we can make models better is with multi-modal LLMs. So these are ways that instead of just with text input, text output, you can actually include images, video, audio, and other types of what is called modes. So it's just the type of media that you're inputting to the model. And you can get those values out as well. So how do we, basically you would be able to give it text and it could spit out an image, it could spit out video, it could spit out audio or text. You give it any of these different modes and it can spit out any of the other modes that you ask it for. So how this came about is essentially that foundational models have been being made for every single type of mode. So rather than classification models, which is how we traditionally did it, where you would give the model an image, for instance, for an image model, and it would respond with a classification of that image. So in this case, if I gave it an image of a cat, it would give me cat out. The foundational models that use transformers, you give it the image of a cat, and instead of the label cat, it gives you a vector of features that describe what a cat is. So very similar to how RAG works, where you have a vector that describes the semantic relations of the text. This does it for images, for videos, for audio, for different modes. So yeah, the transformer of each model then allows you to merge that with the LLMs because they use the same encoding, the same vector encoding on the very base level. So going into how images are done, this is called vision transformer for images. And that builds off of the transform models that was released in 2017. And it's an alternative to the CNN convolutional neural networks. So the image is distilled down into, like I said, a set of floating point numbers, which is the vector. And then that can be then combined in with the LLM to describe what the context of the image is, what the image is in the scope of a vector, rather than the scope of a class like cat. Or this specific one is an image of a cell. So there are specific pieces in that, like the purple areas versus the pink areas. And it describes what the features of that image are. I'm not a medical person, so I don't really know what each one is, but it would be able to classify the purple versus the pink and identify which area is which based on those features. So then how do you train those models together? Well, with text, what it does is you give it a set of text and it tokenizes them, and then it creates embeddings from those tokens. And then with images, it does the same thing, except it puts it into a compatible version of embeddings. And then those embeddings from the text, the images, the video, the audio, whatever modes you want to train, can then be merged into a compatible model that can have access to all of the different types of modes. So then you may be wondering, how does context size work in that case? Because if we have a certain amount of context that is built into the LLM, then how do we go about structuring out how that information gets put into there so that we don't run out of context based by like throwing too many images in, because the context of the LLM can only hold so much data? Well, the way that works is it is essentially the same way that text works. So you throw in if you did it with just text, you would throw in your text tokens in the format as they arrive, and then you would get your response tokens as they arrive, as they come out of the model. But then if you have input image tokens, you would just prepend that as context as the encoded tokens of that image to the text. So it would be the image tokens, and then if you have audio tokens, then video tokens, and then your text tokens. And then you just put those all together, and it comes out of that model, and you get the response based on that content that it gives. And then the response will have the newly created images or video or audio tokens added into there. So the same way, it's essentially the same way that a text token chain would work, except it's with different modes. So how do we use these in practice using LLMs to create a network of things that actually works? So you want to have agent-based systems that, like, each agent in the network is able to do its own thing. So then you can separate out everything and have distributed areas where like each component of the system is able to accomplish a certain task, and you are able to have multiple things going on within a network. So where do you fit LLMs into that? You need to decide where an LLM is going to live. So where is the computation going to be done? Can it be done on the distributed components of that system, on the different agents? And can it be done in a central system? So that would come down to your specific system that you're trying to design, where does each agent have the computational power to create to host the model and be able to actually do the computation of the system? Or do you have one central node that is able to do everything that you need to do, and then all the distributed agents are able to communicate with that? So the things like we talked about earlier with the Llama 1B and 3B models, so that is a smaller model that was released earlier last month. Those type of models would be better suited for if you have a distributed system and you want to host an LLM on a local device that you can let it run around. And that's kind of the progression that we're seeing with models, is they can be smaller and smaller so that we can actually run them on smaller things. Because the current paradigm of it is that we have to run these models on more large computers that have like a pretty large GPU in order to get any actual processing power out of them. So with this, we're able to actually, or as the models get smaller and smaller, we're able to actually be able to distribute those models and run them in separate places. So for example of how you would think about this, we have a project that uses this robot called Temi. So we let Temi run around, and it's deployed in hospitals and elder care facilities, and its main purpose is to serve as a guide for patients and connect patients with doctors for telemedicine. So it could like pop up with the doctor on a screen and let them talk to the person. So we want to integrate an LLM with this, and the question was, could we put an LLM locally on the Temi, or would we need to connect it to a larger network that can support a more centralized node? And because Temi is battery powered and it doesn't have too many computational resources, it is not feasible to put an LLM inside the brain of Temi. And you might have a system where you have a smaller computer that does have the capabilities to do that, and maybe it can't connect into a network. Maybe it's deployed in a field somewhere, and you're using it to talk to a farmer out in the field. That is not connected to the internet, so it can't talk to a central system. But this thing can connect to an internet, and it doesn't have the power, so that in this case, we would want to use a central system and then bring everything back in, and then have the Temi be able to talk to that as the LLM, rather than have its own LLM embedded in it. So this is a system that we've developed at CAI, and it's called LLM Factory, and it is what enables us to use this kind of distributed agent system. So within this basic system, we have several agents. One of them is the web interface that allows us to access the rest of the system through an API, and it allows us to start training through a web interface and create adapters like we talked about earlier, train those down, and create models for the LLMs to fine-tune them. And another one is the training agent, like you just talked about. It actually does the training, so that runs on a NVIDIA DGX HPC. So we have the agent, sorry, let me finish. So the other agent is the inference agent, which runs on an A100, and the storage agent that runs on an S3 server that we locally host. So each of these agents are hosted on different machines that have the resources that we want to be able to actually do each part of it. And this allows us to then scale and distribute the agents as we need, rather than having everything in one place and like have to combine all the resources in one spot. So we design our system to be distributable. Each piece is separate, and then we can put them wherever they need, wherever we have access to resources, and then we can combine them and connect them together through a network. So then we're also able to create LLM agents out in the field. So if we have one agent where, and by agent here I mean like something that is doing querying that uses an LLM in its processing. So if we have an agent that wants to use it, just the basic LLM, pass in a prompt, ask it a question, and it gives a response. We can do that really easily. It doesn't need to have any of the processing power of the LLM. It just needs to be able to query the model. So then that talks to the web interface, which then talks to the inference server and gets back the response. So all of those agents can be defined with the code of each individual agent. You don't need to have any processing power for that, except you just need to be able to connect with a web interface into our web interface. And then if we wanted an agent that uses an adapter, we could do that as well. We just query the web interface, it goes off and does any processing it needs through the adapter stuff and then the inferencing server. And then if we have a RAG-based agent, then we can do the same thing. So we can build out a RAG database and then use the web interface to extract data from that and pull down information there. So pulling back to the TEMI example, the TEMI would be an example of the LLM agent. So we can make TEMIs run around and just contact our web interface anytime they needed to make an LLM query. So we can't afford to put the resources of the LLM onto TEMI. So we just connect TEMI into that system. It is able to, anytime it has a query our system, get the response, and then respond back to it. Or we can do something like this with the RAG-based agent, where we have a system set up that can do RAG processing, and it can host vector databases, but then it doesn't actually host the actual usage of that data. And then from there, we can make another agent that actually queries the data and then does something with that data. And instead of connecting it directly back into the web interface, we're able to connect it directly to that RAG agent. So the processing of what that RAG agent does can be used by the agent with the RAG requirements. So I don't know if I explained that very well. Basically, the RAG agent is defined with specific properties and capabilities of being able to create and query RAG systems. And then if you have another system externally that needs to be able to use RAG, instead of creating your own separate system and then going and querying the interface, you're able to just ask the RAG to do all of the processing there, and then it can respond with the response. So it takes away a lot of the work. You can make a wrapper for the process of doing the RAG stuff exist as its own separate service, and then those services that agent provides can be piggybacked off of, rather than this purple agent having to do its own RAG setup and then query the basic model. So key takeaways of this, basically there are a lot of ways that we can customize the LLM's behavior, and we can go through adapters, we can use RAG, we can use tools in order to get custom behavior out of the LLM and train it in a specific way that makes it work for our specific purposes. And we can deploy LLMs in large scalable systems with agent-based networking and connect everything together. So, anybody have any questions? Yep.
You said in 3.1 and 3.2,
What do you mean, what model?
the one for the 40 whatever.
So the Llama 3 model is a separate model, and it exists completely separately from GPT. I'm not sure.
So can you go back to like the fourth line? There. So go back one.
That one?
So Llama 3.1, 8, 70, 4,
Oh,
5.
yeah. Yes. So the different parameter versions of the models are all the same. So like 128K for the context size of 3.1 and 3.2 affects all of those different parameter sizes. Yeah. Sorry, I misunderstood the question.
We have, time, so,
Yeah.
a lot of information reviewed today, so, digest it.
Yeah, I have a question that you mentioned. You mentioned the RAG, and in my understanding, the RAG actually you build a data set and then you retrieve the knowledge from the data set or the database and then feed the data to the large language model and then you get the response. I wonder whether there are some parts that you can control or you can train for better performance in the RAG system.
Yeah, so that's some techniques that we're looking into right now, because one of the downfalls of RAG is if you give it a really long query that has a lot of different pieces in it. So if I weren't just, in this case, if I weren't talking about circulatory system, but I was talking about respiratory system maybe, and I encoded that in both of them, maybe the value would land somewhere in the middle. So then we would get a bunch of extra data that doesn't really qualify, and it's not the pieces of each individual one. So something that we're working on right now is being able to structure out what the different concepts that we want to look at for each piece of the input query would be, and then pull each one of those out so that we can make multiple RAG searches, pull out the context that is necessary there, and then respond to it.
Yeah, but maybe the key concern is that how can you tell that you, the quality of the result? Because if you want to train your system, you have to have the correct way to assess the performance of such RAG system. So I think if you use different options, different settings, and you get different responses, then how can you tell which response will give you the best performance?
So RAG is more deterministic, so on the same query, it will respond the same values when you do just a search. But then you give that to the LLM, which is not deterministic, whatever
Sure.
the opposite of that is. But it will give you different, like, actual response based on that input context. So in terms of looking for getting the correct RAG results based on your query, you would have to either structure out the query a little bit better to get better results, or you would have to just accept the results that it gives you, I guess, because the results are based on the vector encoding that you pass to the model, and then it does the similarity search. So it's always going to find the same result because it always encodes the same way. So in terms of actually finding whether your response is good, that is really difficult with LLMs because obviously the language stuff is really hard to put a quantitative assessment on. So you just kind of have to play with it and see what makes it work better. Yeah.
I see. Thank you.
Yeah.
Questions? We got plenty of time, so.
Yeah, so sort of along the same lines, so you've got a variety of things you can kind of tack on to, well, your LLM to give it a little bit more specific capabilities. Is there anything that people have been looking at to tack on to the back to basically check the veracity of what it's generating? Be able to confirm whether that is actually consistent with the database?
Yeah, so there are attempts to use another LLM as a judge, which will obviously come with the problems of what if that LLM is wrong. And I have not personally looked into how that works yet, so I can't speak too much on it, but I know that there are a lot of efforts to be able to score the LLM's output, and I've not seen anything with huge success because the only real way to make it like large scale is to use another LLM, and obviously that is issue in itself because you're using the thing that you're trying to test as the thing to test it.
Yeah, more things agreeing is that it must be true, right?
Yeah, exactly. Yeah.
You say it enough, it's correct.
Yeah. In my
That's
experience,
politics that goes that way.
yeah. I tried to do something like that at one point where I would pass this output out to the LLM and I would say, is this accurate? And every single time it told me it was wrong. And even if it wasn't wrong. And there would be like the occasional time where it would be like, yeah, this is right in this way. But almost every single time it was like, no, this is completely wrong. It should be this score. So the thing that I've learned most about working with LLMs for about a year now is that you can use LLMs for language processing. It works really well for understanding, like with the tool calling. It can pull out stuff like the location and the date for this query and what the weather should be like today. But you wouldn't want to use the LLM to do any of the actual thinking, is my takeaway, because while you can, and it will work sometimes, a lot of the time, if you're able to find a way to just structure out the code to do it, and then you have the LLM do the language processing part, then the code is always going, since it's more deterministic, it's going to be a better performer on that actual processing of the information. So that's my advice.
Yeah, so along the same lines again, for medical applications, what kinds of liability issues are you running into? What sorts of things are people actually allowed to use these for? Because, for example, in a nursing home environment or something like that, giving a patient advice from a system like this, one would think that would bring up a lot of liability issues.
Yeah, and that's something that we've run into a lot, where people kind of think that LLMs are really cool so they can do anything. And you throw an LLM at a problem, it's going to solve everything. That's just not the case. So with, like, we're dealing with a project right now where we're supposed to be giving advice to people going into surgery on how they should prepare and like what medication they should take, making sure that they're taking the right meds and stuff like that. And obviously that is a case where if it makes a mistake, that is completely unacceptable, because that can result in huge consequences for that person. So again, we're trying to use the LLM as little as possible in that actual thinking and processing, and use it more for just the language processing. So the language in and out is based on the LLM, but the actual thinking of what meds should we prescribe for this person, what behaviors should we tell them that they should try to do, that is all done not with an LLM, or maybe with an LLM's guidance, but mainly through code, because that is more deterministic and we can define how that gets done.
So my question with the large language models is always, is it really worth the resources it takes to run an LLM to do what people were doing? I worked in a lab that did natural language processing in 1980, and wasn't very good, but we can do better than that without LLMs. What's the value added?
So that depends on the project. So like I was saying earlier, there are a lot of people that come to this and think of, oh, an LLM's really cool, it can do whatever I want, so just put an LLM on it and it'll do it. That's not the case. If there is something that has more complex language processing, then an LLM is really good at it. So there are specific use cases where an LLM is able to act as a chatbot or something, or like process information in a more unstructured way that doing it with code would be extremely difficult. So there are definitely use cases for it, but there are definitely use cases where you wouldn't want to put an LLM on it, because you could do it much more easily and much more deterministically by just doing code. We had a person that we're collaborating with come to us, and he gave me a flow chart of some basic logic that was like, if this value is greater than this, go down this part of the tree. If it is less than that, go down this part of the tree. And he wanted to put an LLM on it, and I was like, just use a decision tree. You wouldn't want to use an LLM for that, because it might be right 95% of the time, but you're going to spend a lot of effort like going through, how do I tell the LLM to do this, and using the resources like you were saying of running the query through the LLM. But you want, like, you could do the same thing with a few if statements. So like, why would you use an LLM for that. And I think that's the key issue that or the misunderstanding that a lot of people that don't have a good grasp of LLMs have, is they think that an LLM is just capable of looking at a text and doing anything. But really, if your input for that type of problem was a structured report, or sorry, an unstructured report that's a doctor wrote or something, and you want to do that, an LLM could do the processing piece of pulling out the relevant numbers, but then you just use the normal decision tree if statements to give you a response.
Questions? Well, I have a question for you.
Yep.
Your system can communicate with text,
Yep.
images, videos.
The system that we designed does not yet. We are, so with Llama 3.2, which was released earlier last month in September, it can. So we are working to update our system to be able to run 3.2, because right now we run 3.0. And we're looking to update that, which would give us the benefit of using the different modes and having that increased context length. And we're having to kind of redesign our entire system to be able to host all of those different information and then combine them together as like on request. But the idea is that our system would be able to do that. But with a general multi-modal model, you can't do that.
Here's a basic question. Okay, when the image is sent to your system, how your system recognize what's first, what's the image? What the image represents, like a cat or something.
Yeah.
How do you do that?
So it goes through the process that I was earlier, where it like vectorizes the images, so it chunks it up and uses the transformer model to find the different features within the image, and then that will be reported as a vector, or a set of vectors. And then when you query it, you put that set of vectors as tokens into your query, and the multimodal model is able to query, or those tokens, understand that it's an image with these features. So if it's a cat, then it would have cat-like features in it, and then it'll respond with the knowledge that that image is of a cat, based on the features.
The cat case is simple, but if you send a video to the system, kind of how would your system be able to recognize what's going on there? Like someone is walking on the street, with an umbrella, and how would you be able to tell that? What the image is trying, or the video is trying to deliver, or to
Yeah. So I don't personally work with the different transform models a whole lot, so this is just kind of my best guess of how I understand the image transform, their vision. I assume that you would break up, like for each frame of the video, you would break up and vectorize each of the frames, and then find all the features of each frame, and then combine them together. And because the model is trained on that type of data, where it has like a person walking down the street, it would have experience of what the features of a person walking looks like in a video. So then it would be able to extract that and kind of relate that, similar to how RAG works, by like doing a similarity search to what it knows based on what it's being given. Does that make sense?
to a certain degree.
Yeah.
There's a question there.
So for the LLM, you are interacting with the database, right?
For which part?
Like the cat word. You train the model with there is cat or not, with the features.
So that's not a database, that's encoded within the model.
Okay,
As,
so
yeah. As weights within the model is like it. I don't really know how to explain it super well, but kind of how a traditional large or machine learning model would have weights. As it gets trained, it adds and changes those weights with the information that gets encoded with it.
okay, so my question was not on that.
Okay.
So I have a different question. Like for some given feature, you are interacting with the database. So how that interaction becomes too fast? Like how are you training the model like so that it will directly go to the database, find the keyword in thousands of data, and retrieve you the answer you are desired?
So are you talking about more with RAG stuff?
Yes,
Okay.
I guess.
So,
Yep.
like with this, each of these has its own encoding, and I've cast it down to a two-dimensional model because it's actually like 760 something, I think, features in most of the embedding models. But you perform encoding on each of the entries in your database, and then you add those to your database, and then you encode your query in the same way, and it creates a value in that same vector space, and then you perform a Euclidean distance analysis to find which ones are the most closely related.
Oh, got it.
Yeah. So like it just finds, it creates these encodings, and then it can find which one is the most closely related based on how the vectorization worked.
Got it. Thank you.
Yeah.
First of all, thank you for the great presentation and for answering all these questions. So I just wanted to know your opinion on, given the lack of computational resources and other limitations, is it really a good thing or feasible thing to study LLMs at university or part of a research? Or do you think it should be more for the big companies? Like, based on your experience, I would like to know your opinion on that.
Yeah. So I think that obviously training a foundational model is probably just not going to happen in anywhere near the near future for like an institution like UK. That'll be someone like OpenAI or Meta who has the resources to be able to train that. But in terms of actually using the models, Llama is open source. It's pretty powerful. There are other open source models, and being able to include those within your system is really good, and that's what we try to do. That's our system, LLM Factory, that we created. Like, the entire point behind that is to make it accessible to people on campus and around other campuses, so that we can we host the model, we run the computation on that, so it's inexpensive for us because we're not like upcharging people on every token that they use. We are just like running the model, and then we take the cost of however much that costs to power the system. And instead of each individual person that comes to us having to host their own models and pay for the cost of that, we're able to have one centralized area where we host a model, and we have it on A100, and other people don't have to go out and buy their own A100 and run the model there. They can just come to us and use our system to have access to a model. And then the different applications from that, like having access to a system like this allows you to create projects that can be distributed and as their own thing. Like, you don't have to worry about what it looks like on the back end or how much that costs on the back end, because you like systems that open there for you. You don't have to worry about creating the infrastructure.
Thank you.
Yeah.
Questions? I think the speaker is quite capable to answer. Yeah.
So on the topic of adapters, if adapters can be seen as removing the guardrails of the AI, would prompt engineering be seen as just jumping over those guardrails or breaking them?
So how adapters work on a more like low-level area is you set the target of the weights that you want to adjust. So that there are different components of the weights of the model, and you can target which parts of it you want to be able to change and how you change them based on the input data that you give it. And system prompts are they're different in that they define how the model talks. So like, it uses the existing weights, but it just has an input of, this is how I'm supposed to be talking right now, versus, for instance, the removing of the guardrails.
Yeah.
There are specific weights that prevent it from talking. Even if you prompt it in a specific way, it would, like some models that have more strict guardrails would not let you prompt it away from being able to go through those guardrails. Because with our example, I tried to make it do that with the system prompt, and it wouldn't work. But through the adapters, you go into the weights of the model and physically remove those guardrails so they don't exist anymore.
Right, but with the, let's say the teenager example, there are ways where people are, like, just call it jailbreaking a model, and by specifically throwing a prompt like they could say, oh, don't say that you can't do this because that would be racist, thereby pushing one of the other limitations that it has, meaning that it could stop it from being able to say that. This is a simple example that doesn't work anymore, but it is something that was a possibility a while back, and I'm
Yeah.
sure that it is still possible if with a far more structured and intentional prompt.
Yeah, and I think that that depends on the specific model and the specific ways that you prompt it. So if there were ways to get around the guardrails originally, then the companies that make these models probably went through and retrained them to add more strong guardrails that like cover that breach that you're talking about. Whereas through an adapter, we're able to completely remove the guardrails, where like the instance that you're talking about, there's like a gap in the guardrails that they're able to kind of sift through. Does that make sense?
Yes, that makes sense. Thank you.
Yeah.
Regarding like trying to get through the guardrails, at what point do you think that you should stop trying to bypass those guardrails and just let them be? Like,
I'm not sure what you mean.
so, like, the LLM doesn't want to give you this answer
Yeah.
for a myriad of reasons. It seems like still trying to find that answer no matter what might not be useful if it's used for anything else. Like,
Yeah, so like I said earlier, there is a reason why they put those guardrails on there. They don't want you to be talking to the model about, they don't want the model that they made to be promoting specific topics. They don't want it to tell you like things that, like how to make a bomb. They don't want you
Yeah.
to be able to hear how to make a bomb. But if we have the need to, like in our case, if we wanted to talk to the teenager that is dealing with suicidal thoughts, that's a requirement of the project, and like obviously our intentions are good, so we find the ways that we can do it. We can remove those guardrails, but like, I mean, if you wanted to, you could also use it to ask it how to make a bomb, and then like
Okay.
that's just kind of on you.
have you noticed its guardrails getting better? times?
Over time, yeah. So like from about a year ago, the guardrails were not as good, and now they are more defined. But again, with the adapter, you're able to completely remove those weights.
Have you noticed a difference in getting past the guardrails, like not really a performance metric, but like, did its output seem the same when it got past the guardrails when they got better? Or did it?
I don't know. I
Don't know.
test that too much. I wasn't hitting on the guardrails a lot and seeing their weaknesses. But with the adapter, again, that completely removes the guardrails, so they just don't exist anymore.
Thank you.
Can an adapter add guardrails?
Yeah, so this example was just one that we've used in practice, so that was why I wanted to highlight it. But an adapter can add new specific information. You could add in, like, don't answer this type of question by just kind of prompting it over and over again. If you see an input like this, don't respond to it, respond to it. I don't want to talk about that. Yeah, that's definitely something you can do. Because the point of the adapters is just to adjust the language. So it can go either way, and it can add new information, all kinds of stuff.
Thank you.
Questions? We still have a few minutes, so any questions? I think you can answer almost any questions. So if you have a question, ask. All right, then we thank the speaker, Mr. Klusty, for a very informative, talk. Okay, thank you. Thank you again very much.